Hello, thanks for attending my presentation today. I'm Chris Bender, and I'm going to be speaking about a modified linear superposition method for the interaction of tide and storm surge. This is work that my co-authors Ashley Coppola and Don Riccio have been working on, and we're excited to present it to you. For a brief outline, I'll provide background information and then move into why the interaction of storm surge and tides is important. I'll discuss the area of study that we looked at and provide some details on the development of the MLS approach. I'll show some results, discuss some future plans, and hopefully we'll have some time for questions at the end. So, extratropical cyclones, also known as nor'easters, can produce elevated water levels that persist for multiple tidal cycles due to their large size, the movement, and also their wind field structure. For regions that experience a large tide range and extratropical storm forcing, the interaction of the surge and tides is important for the total water levels that develop and the nonlinear interaction that can occur between the tides and the surges. Several different methods have been developed to calculate the combined storm surge and tidal water levels. However, not all of them appropriately account for the nonlinear interaction or do so in a robust way that's appropriate for when high-resolution numerical models are applied and the number of runs that are possible to complete during a study are relatively limited. So as an example of one of these storm surge patterns that can occur for an extratropical cyclone, we have a plot of the water surface elevation versus time for an event that occurred in 1950, and this is the water level at the Battery near New York City. So we see the tidal variation and then the long duration of the elevated water levels that occur over an extended duration that with the interaction of the tides occurring with the storm surge during this time. And these extratropical cyclones can occur several times or more during the course of a year along the United States mid-Atlantic coast. So they are quite frequent and are important to study. The focus area for our examination was the New York and New Jersey coastline along the U.S. mid-Atlantic coast in an area that features a relatively complicated coastal topography with large bays such as Delaware Bay, New York Harbor. We have the Long Island Sound feature, as well as smaller back bay areas which occur along the New Jersey coast where we have several inlets with smaller bay features behind those inlets. And these features are important because they have different features for the interaction of the storm surge with the tides. Having a robust and efficient way to include this nonlinear interaction of the storm surge and tides is important when conducting a regional storm surge study for a region such as this. So for the development of the MLS approach, we applied SWAN+ADCIRC model results related to a Federal Emergency Management Agency, or FEMA, coastal storm surge study. The study area included the New Jersey coastline and the area near New York City, and for the analysis that was completed several years ago, a suite of 30 extratropical cyclones was applied, where each of the cyclones was executed at 4 different tide phases. 2 tide phases occurred near high tide and 2 occurred near low tide. And using these results, the prior study estimated the interaction of the surge with the tides and developed a water level versus frequency curve for the extratropical storm forcing. Importantly, the analysis required that each of the 30 cyclones within the storm suite had to be executed at multiple tide phases, in this case 4. But it's not known whether 6 or 8 or 10 or how many would be needed to really understand the interaction of the surge with the tidal forcing for the number of different phases that might be needed. For the MLS approach that was developed, the intent was to have a more efficient way where only a subset of this suite of extratropical cyclones would be needed to have an execution for multiple tide phases. So the MLS analysis picked 8 of the 30 extratropical cyclones and examined the tide-only simulation, the extratropical storm forcing only simulation, so winds and pressure fields but no tides, and then the coupled storm and tide model. And we examined those in order to develop the nonlinear deviation in the surge and tides. So this was the difference between the fully coupled model result, the maximum water level that occurred during that, which includes the physics of the tides interacting with the surge. We compared that with a simple linear superposition method that added the tide-only run with the storm-only run and the maximum water level that occurred when we simply added those together. So the difference between those two was the nonlinear deviation, and we developed that for a subset of points that I'll get into in a minute. And then what we are able to do then is to include that nonlinear deviation over thousands. In this case, we did over 5,000 tide starts to account for how that nonlinear deviation would influence the linear superposition water level if we started the tide at any number of times during the storm or vice versa, when that interaction was aligned in different ways. So the goals were to remove the deterministic variation in this nonlinear deviation, as well as being able to retain data to quantify the uncertainty for the unexplained variation within the analysis. So we focused on 34 stations along the New York and New Jersey coastline, and it might be hard to see the details, but the important point is that we had stations along the open coast, we had stations within the bays and New York Harbor, as well as Long Island Sound, and then we had stations in the New Jersey Back Bay areas, as well as some of the small channels near New York City. So we were able to examine the features in the nonlinear deviation for these different areas, as well as how the MLS approach was able to modify and develop the water level versus frequency curve in these areas. We focused on two stations for this presentation. One is Point 15, which is located along the open coast in Monmouth County, New Jersey, in the northern part of New Jersey. And then Point 17, which is in one of these Back Bay areas that has a long axis in the north-south direction, and it's actually located and even within a smaller embayment off of that. So we focused on those two locations in order to show the difference in the MLS results. So within the MLS approach, we examined results for the 8 storms that were selected. Each was run at 4 tide phases, so we have 32 data points that show the nonlinear deviation at the maximum linear superposition total water level on the y-axis, and then the maximum linear superposition total water level along the x-axis. And for point 15 along the open coast, we see this trend of decreasing nonlinear deviation as the maximum linear superposition total water level increases. And we see a relatively tight fit kind of within that trend. If we look at station 17 in the lower plot along the interior Back Bay area, we see much more scatter in the nonlinear deviation, and we also see smaller values in the maximum linear superposition total water level in a larger kind of clustering by individual storms than we had for the open coast station, station 15. We examine the results at station 15 in a bit more detail. The next step in the MLS approach was to normalize the linear superposition total water level and develop plots with using that along the x-axis and the nonlinear deviation along the y-axis. So this normalization was done by calculating the average maximum total water level across all possible tide and surge combinations within a 2-month tide run. So with that 2-month tide run and having data points every 15 minutes, we end up with over 5,000 different tide starts that are possible. And we found the maximum linear superposition total water level for each of those over 5,000 tide starts and then took the average value. That allowed us to have a value at each station to normalize with, and it takes into account the fact that there's a larger tide range in Long Island Sound than we have along the open coast in New Jersey, and then there's an even smaller tide range in those back bay areas. So having that normalizing factor allowed us to create plots that are centered or close to centered on a value of 1 on that normalized axis for each station. And then within each of these plots, we developed a regression line to develop the coefficients with which we would use to adjust the linear superposition water levels to correct for the nonlinear deviation. So this is the result at station 15 for that regression line. And then we're able to correct the results for the MLS method. So instead of just a simple linear superposition, which are the x's, we have a correction, which then results in values that are longer to the, or closer to the true line, where our linear superposition maximum total water level would match the coupled SWAN+ADCIRC model result that includes both forces. We can also do the same, create the same plots for station 17. In this case, we get an increasing trend, but with more scatter for the nonlinear deviation versus the normalized linear superposition total water level. And then we can apply that correction for our 32 instances that we have. So the end result of this is, with those regression lines for each of our stations, we are able to apply a correction at each station for all possible 5,000 tide starts for each of the 30 stations. So even though we only used a subset of 8 stations to create the regression line, we apply that relationship for all 30 of the storms that we have within our storm suite. And knowing that we had 30 storms within an approximately 60-year period, we can do a frequency analysis based on those 30 results and develop a water level versus annual exceedance probability curve, where if we just used a linear superposition result, we have the red dashed line, and if we apply the MLS correction, we get the blue line. The circles represent the fact that at each of those 30 storms, we have a maximum total water level out of our 5,000 different tide starts, and we also have a minimum maximum water level out of those 5,000 tide starts. This allows us to bracket where those results would be, and it shows the sensitivity to where if you were to randomly pick 4 or 6 or 8 tide phases, you may hit one of those extreme values. So for conclusions, we've developed the MLS approach to develop to account for nonlinear action between extratropical cyclone surges and tides. We apply a previously created data set for a mid-Atlantic coast case study area. The process works by developing regression lines at selected points to account for the nonlinear interaction, and then we apply those regression coefficients to correct a simple linear superposition result to create a value that accounts for the nonlinear interaction. Future applications for this could include looking at tropical cyclones, which have a much narrower peak storm surge, and but also higher storm surges. So that would be something that we could look into. Thank you for your time. I have time for some questions.